Hi, my name is Anurag Sakhar, and this is my final coursework for the module Mobile Robotic PD 4430. So basically, I'll be representing my project on designing a mobile robot that can interact with its environment in a simulation, specifically focusing on flap teleoperation and movement in Gazebo. So in this project, I've created a custom robot using ROS2 and Gazebo for simulation. The robot called Flap TV3 bot is designed to move spheres within a bounded area equipped with sensors and flaps to manipulate objects in the environment. So let's start with the design first. Basically, my Zacro file here called flaptv3.underscore bot.zacro is based on a differential drive model with the two main wheels, a caster wheel for support and two flaps on the sides for object manipulation. In terms of hardware, the robot includes a LiDAR sensor for mapping, a camera for visual feedback, and two flaps that are controlled in real time for precise interaction with the objects that are spheres in our case. Um, Here is basically the key code structure used for this project. I've created the Zacro, which defines robot physical properties. Every link has also inertial values and material that is being used to give color to the physical parts. And in addition to this, in the end, I have Gazebo plugins that are used basically for the joint state and the joint state publisher, and also the position controller system for the flaps. Similarly, odometry for the ODOM baselink transform TX. So basically in the simulation, the URDF is added into Gazebo, and you can see the robot moving and interacting with the environment. Now let's dive into the technical aspects of the project. The robot's movement is controlled using a differential drive system, which are where our wheels are commanded via ROS messages. The flaps are controlled using the simple teleoperation script, which I have a separate package, and this script is flap teleop node. Um, when you press certain keys in the keyboard, the flap angles change, allowing the robot to interact with objects such as pushing spheres, not push grabbing spheres. The Gazebo simulation runs with ROS2, and the robot slider and camera feed information into the navigation system, allowing for basic obstacle avoidance. The teleoperation system for the flaps is quite simple. It allows for precise control, opening or closing the left and right flaps by pressing keys such as the Z to close the left flap and A to open it. Similarly, press X and S to controls for the right flap. Um, as I've mentioned in this Python script. Now I'll demonstrate how the robot moves and interacts in the simulation. I'll first launch the system, and you'll see the robot appear in Gazebo, and then we'll use commands to move it around, open and close flaps. So as you can see, the robot is loaded, and so similarly is the assessment world. Now, if I go and launch and start the teleop with keyboard node, it will allow me to move the robot in real time using the I, J, and K commands. I for moving forward, K for stopping, and J and L for moving left and right. Similarly, if I launch the teleop node, it will allow me to open and close the flaps. So as you can see, it is allowing me to control both the left and right flaps to adjust according to the diameter of the sphere, whichever at that moment you have to uh, grab. Um, As you can see, the robot's flaps are able to manipulate to sphere effectively by adjusting their angles. The control is responsive and smooth, allowing the robot to move the sphere towards the designated goal. In this link, I will also be adding a link for the complete teleoperation process, which takes a lot longer if I had to include it in the same video. So now let's move on to the localization and navigation aspect of the project. Using ROS2's nav2 stack, I've configured the robot to navigate autonomously within a predefined map. So initially, I used the SLAM toolbox plugin to generate a map by setting the mode room mapping in the slam params.yaml file. And the simultaneous localization and mapping SLAM was used for the map creation. The LiDAR sensor scanned the environment, and AMCL was used for localization within the map. The map was then saved in a maps folder within the mobile robot package as my map save the YAML and PGM files. And this same file was then used for the navigation process. So once the map was saved, we shifted the mode to localization. I added the map file name with the path where the map was saved, and map started doc will true. Once that was done, the navigation process was I was able to do that. So now I'll be showing you a demonstration of that. So we will use a slam.launch file to open up Gazebo, spawn the robot with the assessment world, the spheres, and also open up Arvis. So as you can see, um, Gazebo is loading up. And now it has spawned the robot, the three different affairs, and in the assessment world. And I've also set the RWIS in the autom fixed frame with the robot model, the TF, the laser scan already already there. And I also added a camera for the ball detection, but currently the ball detection isn't working, so we will just be closing these two. um Next up, we will add a map and first load the generated map. And once we're done with that, then we'll be loading the global cost map. So in the map, we'll set the map topic to map where it's being published, and then we'll be using the nav to bring up a localization launch file with the path of where our map is safe to load up the predefined map. So this starts all the known required, and once that is done, it asks us to set the initial pose to align the predefined map with the laser scan that is being shown in real time. And that's for that we'll be hopping into the map frame, and then using 2D pose estimate to set the initial pose. Now we need to make sure that the initial pose is set correctly, as that will allow the better navigation of the robot. Right. Once that is done, we need to set the map topic to transient local for the map to show up. Yeah. As you can see, now the laser scanner almost above the predefined map, and this right here is the ball that wasn't part of the slam toolbox when we were creating a map. So once we're in the navigation part, we can also visualize this laser scan can also visualize obstacles that weren't available in the original predefined map or the original assessment world. So it can cater to any obstacles that appear afterwards. Okay, now that our robot has been localized in the predefined map, we now need to navigate through it. So we will be using the nav to bring up navigation launch file, which will subscribe to the transient local that we just set. And after launching this, it will basically help us generate a cost map. So cost map basically defines cost to different parts of the map. The higher the cost, the more the robot does not go to that area, and the lower the cost, the more the robot finds that a safer place to be. So as you can see, now that I've started that the navigation launch file, we will now be using the global map topic to introduce the cost map right here, setting the color scheme of the cost map. So basically, the closer the obstacle, the more the color of the robot will be to not go near it. Yeah. So as you can see, the closer the color to the obstacle is red, and the further away it starts to go blue, which means blue for the robot is an area where it can meet. For navigation, now we can use the goal 2D goalpost to set any orientation and position of the robot. So basically, what this arrow does is you can set the coordinates, the position, and the orientation where it will point. And so the robot accordingly first understand accordingly based on the cost map moves from one place to another and plans the path on its own. Um, and this can also be seen in the in Gazebo as the robot moves. Similarly, you can see that now that the spheres are here, and when the map was generated, the spheres weren't there. So the laser scan in real time will give us the obstacles that are the spheres now, the location of those obstacles, and as the robot moves to that position, it will kind of generate a temporary map for the obstacles that are being generated. So this helps the robot path plan in real time as well. Currently, it does not know because the ball moves. It does not know to not touch the obstacles, and so you can see that the red ball is moving. Um, mm, but it does reach the final position that it was initially assigned to move to. And in the terminal, it also shows that the goal succeeded. So basically, it has reached its final position. You can also use the navigation panel to kind of set predefined waypoints, and so the robot moves accordingly. Um, so it doesn't stop between 2 or 3 points or as many as you want to add. So you use this waypoint through pose mode to set waypoints. So in conclusion, this project demonstrates the design functionality of a mobile robot capable of manipulating objects using teleoperation, navigating autonomously, and interacting with the environment of a gazebo simulation. Right now, the detection of the balls using the camera and giving its coordinates back and moving the robot accordingly is not working. But currently, the camera works. It gives us a live. It gives us a real time visuals of this response affairs within the assessment world. And it is also using the LiDAR data in real time, able to navigate uh, autonomously within the predefined map. Um, and also the teleoperated flaps have also been integrated for movement of spheres from different positions to the pen. In the future, I plan to enhance the system by incorporating full autonomous object manipulation and more advanced SLAM capabilities. Thank you.